Welcome back. In this video, we talk about deep neural networks. A deep network is the same as the densely connected feed-forward neural network we've looked at before. It just has more hidden layers. That's what makes it deep. Deep learning has achieved remarkable results in many domains over the past few years. Deep learning requires more data and more processing power. Fortunately, cloud services like Google Colab can provide the processing power that your local machine may lack. One other thing that deep learning requires is highly efficient libraries. In this video, we look at one such library, Keras. Here's the main page for Keras, keras.io. The main point of the Keras API is to provide you a very good and simple API that will enable you to try different things quickly. Notice you can access the API here or guides here. The documentation is just terrific. Keras was released originally in March 2015 as a deep learning API that could run on top of TensorFlow, Theano, or other deep learning libraries. The Keras API allows a great deal of flexibility in designing networks, in terms of the layers, loss functions, optimizations, and so forth. Keras 2 was released in 2017 and is now integrated with TensorFlow. So going forward, Keras will have two implementations. One is the standalone Keras API, which can run on top of either TensorFlow, Theano, or other backends. And the other Keras implementation is incorporated within TensorFlow and is available as tf.keras. This blog link here introduces some of the differences. This blog post is by Francois Chalot. He developed Keras when he was an AI researcher at Google. He's still there at Google, and he's still instrumental in the development of Keras. If you have a GPU on your system, there are specific instructions for installing Keras. Otherwise, you can just use pip or pip3 install TensorFlow, which will install TensorFlow as well as tf-keras. You can also find a lot of documentation on the TensorFlow site. The basic data type in TensorFlow is the tensor. Tensors are multidimensional arrays. Here's some illustrations with a uniform type. Tensors are kind of like NumPy arrays. All tensors are immutable. You can't update the contents of a tensor, only create a new one. And the under-the-hood advantage of making tensors immutable is that they can be made more memory efficient and time efficient. Let's look at an example from the GitHub to see what the code looks like. I'm going to import TensorFlow, and from TensorFlow.keras preprocessing, I'm going to import the tokenizer and do my text preprocessing with Keras instead of sklearn. I also need to import layers and models. So each layer represents one transformation step in a multi-layer deep network. The model defines how the layers work together. The most basic model is the sequential model, which is just a linear stack of layers. Think of the sequential model as just a regular feed-forward neural network. It just has a new name here in Keras. I'm importing my data as usual. Here I'm just using NumPy to divide between train and test very simply. I have some parameters here that I'll need. The number of labels in my target is 2. This is a binary classification. I'm going to limit the vocabulary to the most frequent 25,000 words. And I'm going to use a batch size of 100. So recall we had an earlier discussion of stochastic gradient descent. Rather than using gradient descent or any other optimization on all of the data at once, we take it a batch at a time. These lines of code next will prepare the data. First, I'm setting up Keras' tokenizer. Then I'm going to fit it on the training data. Once I've fitted on the training data, I can apply it to both train and test to convert those to matrix. This is just an alternative to the way that we've done this before in sklearn. You can use sklearn as well. These next lines will encode the labels. And here I'm just printing out the shape. Next, I'm going to build a model. I talked about Keras having two different implementations going forward. That means it has two different syntaxes. This is more of the traditional Keras syntax. In later notebooks, I'll show the tf.keras syntax. This box shows the 3 steps that you go through. The first is to build the model. Those are these steps here. The second is to compile the model. And the third is to actually fit the model, do the training. Let's look at the first step here. We're letting model be our variable that holds the model that we're constructing. We want it to be a sequential feed-forward network. We have only one hidden layer here of 32 nodes. Our activation is ReLU. Then we have a final output layer of 1 node with sigmoid activation. After we build a model, we have to compile it, and we need to tell it 3 different parameters. We need to specify our loss function, what kind of optimizer we want, and our metrics to use during training. Since this is a binary classification problem, we'll use binary cross-entropy. Atom is a good solver, a general purpose solver. There's more about that in the chapter. The metric we can use during training is accuracy. And then we fit. We give it our training data, specify a batch size, tell it to train for 30 epochs, so 30 forward-backward passes. There's different options for how much output you want, and we tell it to pick off 10% of this training data for validation. So I'm going to hit run so we can see how fast or slow this is. Pretty fast, and you can see our validation accuracy going up over the epochs, and then it seems to kind of stall out here. We'll talk more about that in future notebooks. We can evaluate, and we see we got an accuracy of 0.985, almost 99%. We can also print out the score. Here I'm just showing how to extract some predictors, and we can see that these are the probabilities. We can also just extract the labels. And one of the nice things about Keras is that it incorporates well with a lot of functionality from NumPy, Pandas, and sklearn. Here I'm going to use the sklearn metrics to print out some accuracy information. So straight out of the box there, we got really good results. This next example is taken from Chalot's book, Deep Learning with Python. Here's a link here. You can find it anywhere. He's currently writing the 2nd edition, so if you're interested, I would wait and get the 2nd edition. Manning Publications has this MEEP program where you can buy the book before it's actually finished. And you can see here what's been finished and what he's still working on. As he adds new chapters, you'll get an update from Manning. Download the newest version of the PDF. Back to our notebook. The book also has a GitHub with a lot of great sample projects. This notebook uses the built-in movie data set. It's in Keras already. Importing TensorFlow, and this time in addition to importing layers and models, I'm importing data sets so I can grab that data set. I'm giving it a parameter that I only want the top 10,000 words. This is my current TensorFlow version. And the data set is already pre-divided into 25,000 training examples and 25,000 test examples. This is yet another way to vectorize the data. First, we create a zero field matrix and then set a binary 1-0 indicator if a given sample has that word, and then vectorize those. Also vectorize the label. There's many different ways to do things in Keras and TensorFlow, and that can be a little bit overwhelming at first. In this notebook, I've divided those 3 steps of building the model, compiling, and then training. I've divided those into different text boxes here. This sequential model is going to have 2 hidden layers here in the middle, 16 nodes in each one. And again, because it's a binary classification, we'll have one final output layer, one final node with sigmoid activation. We use the dense layer for the regular feed-forward neural network. This time I'm using a different optimizer. It's a variation of backpropagation. And I'm also going to manually pick off some validation data to use during training. I specify those here. I specified batch size quite a bit larger this time and just 20 epochs. So let's see how long that takes to train. See our accuracy going up. The accuracy on that training validation went quite high. You do have to worry about overfitting. Let's do the classification report, and we see we got an accuracy of about 85%. This is another way to extract the predictions. And now I'm going to plot. Let me back up here. Okay, notice here that this history variable is going to point to all the information learned during training. So down here, we can actually plot that. We can plot our training loss and our validation loss. And we see that after a certain point, we're probably overfitting. We're doing better and better on the training data and worse on our validation data. So this is overfitting going on here. This is another way to look at it. We're seeing the same story. So what we could do is we could plot this and then manually decide how many epochs we want. But we can also use an early stopping feature within Keras that will enable the algorithm itself to figure out when it's overtraining. And we see that training was much shorter here. And let's print out our results. Results are about the same, actually. I'm going to show you one more notebook. It's actually the same as the notebook we just went over about the movie data, but I'm going to use the functional API syntax just to show you the difference. So the beginning part of the notebook is exactly the same until we get down to where we want to define our model. So defining the model in the Keras notation is really clean and easy to read. This looks even worse than it is because I've put all of this in different boxes here to explain each step. We'll have to define the inputs, add our layers, define the output layer, and put it all together. All right, so let's go through those one by one. We set up an input layer given our shape. We don't specify the number of training examples either in this syntax or this one because Keras will just figure that out. But here we're specifying that each sample has 10,000 input features. Next, we explicitly add a dense layer, and we're letting X be that input layer plus the dense layer, and then we can just keep adding to X. So here we're adding the other dense layer. Finally, we're adding the outputs. And then we put it all together in this syntax here. Keras.model, specify our inputs and our outputs, our outputs, remember, now includes all of those layers. And we actually gave it a name. So this syntax is not very pleasing to me compared to this syntax, but the advantage of it, once you get used to it, is that it's actually has a lot more options in there. The rest of this is going to be the same as usual, so I won't show that. I will show summary. You can do this with either syntax. You just say model.summary, and it gives you a nice summary of what's going on here of your model, the different layers that you have, and the number of parameters it's going to learn. Using the same fit here, I just went ahead and chopped it off at 4. Interestingly, when I chopped it off at 4, instead of using like last time, we used this early stopping feature. Here, I just manually cut it off at 4, and it looks like I got a little bit better accuracy. One more thing I want to show in this notebook is that you can save your model after you build it. Getting some kind of warning here. And it tells me where it saved the model. If I look at my sidebar, I see that it saved it right here. And just to prove to ourselves that that really did work, I'm going to delete it from working memory. Then I'm going to reload it, and then just do the summary one more time to show that it's the same model. So the advantage of this is that if you have some code that trains the model and it takes a really long time, once you save that model, you can use that again on new test data. So we've seen that whichever syntax we use, either the Keras or the TF Keras, we've got a certain workflow. We define our model, compile it, fit it, and then we evaluate the results. The results that we got in either of these notebooks weren't really spectacular, and that's probably what you'll encounter the first time you run through. So there's all kinds of parameters within the models themselves that you can change. There's different ways of pre-processing the data that may have a significant effect on the outcome. But we're just getting our feet wet here, and we've learned how to build a model with both the Keras API and the Functional API in TensorFlow. And the notebooks going forward may use either approach. And I'm going to leave you today with a quote from Mav's owner, Mark Cuban. Artificial intelligence, deep learning, machine learning, whatever you're doing, if you don't understand it, learn it, because otherwise you're going to be a dinosaur within 3 years.